Hi everyone, my name is Elenora van Rijsingen. I'm a postdoc at École Normale Supérieure in Paris, and I'm working with Eric Calais and Romain Jolivet on the Seismotectonics of the Lesser Antilles subduction. So the results that I will show here today are related to the interseismic coupling of this subduction zone, and we will actually show you that this subduction zone currently has a low coupling. So the Lesser Antilles forms the eastern boundary of the Caribbean plate, which moves with a velocity of about 2 centimeters per year towards the north-northeast, overriding the North and South American plate that subduct towards the west. So the Lesser Antilles forms a global end member, not only because of the slow convergence, but also because old lithosphere is subducting with an age of about 80 to 100 million years. And the subduction lithosphere is also slow spread lithosphere, formed along a slow spreading ridge and therefore more pervasively hydrated and fractured compared to lithosphere that formed along faster spreading ridges, such as in the Pacific. So if we look at a bit more detail into the characteristics of the subduction zone, we see some differences between the north and the south. So in the north, the forearc is characterized by trench perpendicular normal faults that indicate trench parallel extension, while the southern part is characterized by this Barbados accretionary prism that is fed by sediments coming from Venezuela, from the Orinoco River. Also, in terms of small, shallow seismicity, we see a difference between the north and the south, where the north is much more abundant in this shallow, small seismicity. If we look at the larger event that occurred within the instrumental record, all the largest events are normal faulting earthquakes that occurred either within the downgoing plate at shallow or intermediate depths, or within the overriding plate, such as the 1974 earthquake. So there's two historical earthquakes that occurred in 1839 and 1843 that have been proposed to have occurred along the subduction interface. So here you see the proposed rupture contours of these two historical earthquakes, which are offshore Martinique, Dominica, and Guadeloupe. So a difficulty with historical earthquakes is that we don't have any seismic data. So in order to understand what the magnitude was of these events, we need to rely on eyewitness descriptions, which can be letters or newspaper articles or other type of reports from those times. So from these descriptions, intensity maps can be made showing the distribution of different levels of damage after the event, and these can be used to derive an estimate of the magnitude. So the magnitude estimates for the 1839 event range from 7 to 8, and for the 1843 event, they range from 7.5 to 8.5. So there's a bit of uncertainty in these estimates, but one thing that is certain is that these events were relatively large, or even for the 1843, very large. So another difficulty with these historical earthquakes is the fact that we don't know where they occurred exactly. So with the information that we have, we can actually not say whether they occurred along the subduction interface or maybe somewhere else within the subduction zone. So that makes it extra challenging. So to sum up what we know about the seismicity in the Lesser Antilles, we in the instrumental record, we only see large infraplate events, either within the overriding plate or in the downgoing plate, such as this 7.3 2007 earthquake. And the big question here is what happens along the interface? Did very large earthquakes occur along the subduction interface in the past, such as these 1843 and 1839 events? And can we expect such large events to occur along the interface in the future? So GPS observations can be very useful to provide more information about what's happening along the subduction interface, as they can actually measure how much elastic strain is being built up along the interface as the downgoing plate subducts. So Symithe and co-authors in 2015 used GPS observations in the Antilles to derive the interseismic coupling for both the Lesser and the Greater Antilles, and they found low coupling in the Lesser Antilles and higher coupling towards the Greater Antilles. So there's quite a few uncertainties related to this approach, which is related to the distance between the trench and the stations, the non-uniqueness of the inversion, but also the fact that they used a planar subduction interface with a constant dip angle of 16 degrees for the Lesser Antilles, and they also assumed a down dip limit of 40 kilometers. We now have much more information about the actual geometry of the subduction interface, which actually varies along strike. And we also know that the down-dip limit of the seismogenic zone probably extended deeper, maybe even down to 65 kilometers depth, which was indicated by this cold mantle wedge corner, and also the fact that a magnitude 5.8 thrust earthquake occurred at about 50 kilometers depth. So what we aimed to do was use updated GPS velocities and more detailed information about both the slab geometry, but also the elastic structure, to provide interseismic coupling in a more rigorous way. So we also try to better take into account the uncertainties that are related to the inversion by using a Bayesian approach. So here you see the distribution of our data, both in the Caribbean and a North American reference frame. So we have 74 stations that are distributed along the arc. The majority of these stations are continuous stations. And as you can see, the highest density of stations is in the central part of the arc on the islands of Martinique and Guadeloupe. So like I said, we aim to infer the interseismic coupling using a Bayesian approach. So the data measured at the surface can be related to a slip that is modeled along the fault using this forward problem, D equals G times M, where D represents the data vector with GPS observations, G the Green's functions matrix that relates the interseismic coupling to the surface displacement, and M the model vector. So the goal is to infer the distribution of model parameters M that is consistent with our data D. So because of uncertainties both in the data and in the model, but also the uneven distribution of stations, the solution to this problem is non-unique. So therefore, instead of deriving a single solution, we explore the entire range of possible models to provide a probabilistic estimate of interseismic coupling. So the models that fit the data and are consistent with our prior constraints can be described as full posterior probability density functions. So they can be described like this following Bayes' theorem. So we assume a uniform prior between 0 and 1, meaning that we don't assume any prior knowledge on the model parameters, and we assume an equal likelihood for all the coupling values between 0 and 1. And so because we deal with this high dimensional space, we actually sample the posterior PDF using ALTAR, which is a parallel Markov chain Monte Carlo algorithm based on CATNIP. So like I said, instead of deriving a single solution, we end up with an ensemble of 150,000 models that are drawn from this posterior PDF. So before I show you the results, one thing we can do is look at how well our data can indicate what is happening along the subduction interface. So this can be described using the sensitivity. So the sensitivity basically shows the relative contribution of each fault node to the surface displacements or to the predictions, the model predictions. So sensitivity is generally expected to be low further away from the data points and higher closer to the data points. And this is basically what we see. So we see low sensitivity in the shallow parts of the fault, especially towards the south, where the distance between the stations and the trench is larger. And we see higher sensitivity in the central part of the fault between depths of about 25 to 60 kilometers. And this area where we have the highest sensitivity coincides with these proposed rupture contours for the 1839 and 1843 earthquakes. So here I show you the results of our posterior coupling model. So like I said, we have an ensemble of 150,000 models, which we can visualize by plotting, for example, the mean or the mode of our posterior model. So here on the left, you see the mean model, which generally indicates low to very low coupling along almost the entire interface. In the central part of the fault, where we have the highest sensitivity, mean coupling values are very close to 0, while in the shallower parts, where the sensitivity is also a bit lower, you see that the mean coupling is more towards 0.2. Then there's these two deep nodes that show localized values of higher coupling. So around Martinique, this is a mean coupling of 0.5, and here around the Grenadines, this is 0.6 to 0.7. So these two deep nodes are located at a depth of 100 kilometers. So this is well below the down dip limit of the seismogenic zone. So we believe that these two deep nodes of slightly higher coupling are related to an artifact of the model where it tries to fit southward displacements on the islands above. And the southward displacements are probably related to extension, arc parallel extension that is occurring in the overriding plate. So we can also look at the mode, like I said. So here on the right, you see the mode model, which basically shows zero coupling everywhere except for these two deep nodes that I just explained to you. So the mode and the mean don't tell the whole story because they don't show how much our model has evolved from our uniform prior with a mean of 0.5. So in order to better understand what the distributions are for specific nodes, we can plot these marginal PDFs. So here you see the probability density functions for specific nodes along the fault. So node 1, 2, and 5 are all relatively narrow towards 0, indicating that they've evolved more from this uniform prior with a mean of 0.5, and that this low coupling is relatively well constrained. So the node that I just talked to you about, this deep node around Martinique, number 3, has a much wider distribution with a mean around 0.5, and this shows that it actually has evolved less from our uniform prior. And this makes sense because this node is relatively deep, so it also has a lower sensitivity than the more shallower nodes. So we are quite lucky because recently different models of the fault geometry have been published. So the results that I showed you before are related to the SLAB2 model. But this year, B and co-authors also published a slightly different geometry of the subducting slab in this region. And here on the bottom, you see 3 different depth profiles where you can compare the geometry of the 2 different models. So as you can see, at higher depths, the B et al. Model is quite a bit steeper and actually fits the local seismicity better. And if you look at depth, seismogenic depth ranges, you see that the 2 models are more similar. And this is also what we see when we perform this Bayesian inversion for both the fault geometries. We see a very similar pattern of mean interseismic coupling with especially very low to low coupling in the central parts of the fault. So one thing we wanted to test is something specifically related to these historical earthquakes. So we wanted to test that if 170 years after these events occurred, assuming that they occurred along the subduction interface, whether we would see relocking in these areas. So what we did is we synthetically locked these proposed rupture areas for these 2 historical events. We predicted surface displacements from these synthetic locking models and used these data as input for the Bayesian inversion. So as you can see, we can resolve these areas of high coupling relatively well, not perfect, and this is mainly related to the fact that we use a refined mesh for the input model to correctly lock the proposed rupture area of this earthquake, while when we do the Bayesian inversion, we wanted to keep the same fault mesh as we've done before. So yeah, the coupling is quite well resolved. You see that there's some shallow areas that also show higher coupling, which is not in the input, and this is related to this lower sensitivity and the fact that in the shallowest parts of the fault we can actually say less about what's happening because we're further away from our stations. So what this test shows that if these historical earthquakes occurred along the subduction interface, and if they had relocked in the last 170 years, we should first of all see that in the data, in the GPS data on the islands, and therefore also see it in the coupling inversion, and we don't see that. So it's quite unlikely that there's some relocking occurring in these areas currently. So this raises questions about the nature of these 2 historical earthquakes. We find currently low coupling along the interface. Actually, there's no tsunami observations for these 2 historical earthquakes. So perhaps they had either a smaller magnitude, or maybe they occurred at different depths. Maybe they had a different faulting mechanism and were similar to some of the other relatively large intermediate depth earthquakes that we've seen. So this is definitely something that we should look at in the future. So the main result of our study is that we find a current low coupling along almost the entire subduction interface. So we tried to think of parameters that could explain this low coupling. So some of the characteristics of this region are the slow convergence of relatively old lithosphere, the extension in the overriding plate. We have several features subducting, such as fracture zones, but also several ridges. There's a large amounts of trench sediments in the south, and there's this hydrated, slow spread oceanic lithosphere. So since we do not see any large variations in interseismic coupling along strike, it is quite unlikely that localized features such as ridges or fracture zones play a dominant role here. And the same holds for the differences between the north and the south, because we don't see a clear difference in coupling between the north and the south. So we propose that perhaps in this region there's more like a margin-wide parameter that is tuning the seismogenic behavior of this region and causing this low interseismic coupling. So one possibility could be this highly hydrated and fractured incoming lithosphere that brings fluid to the subduction interface, increasing the pore pressure and therefore reducing the effective normal stress, and possibly promoting a more stable sliding creep-like behavior on the interface. So the main conclusion of this work is that we find low to very low coupling along the entire plate interface, including these proposed rupture areas of these historical earthquakes where we have the highest sensitivity. So one thing I would like to note is that even though these results indicate that large megathrust events are quite unlikely or rare in this region, it doesn't mean that there's no seismic hazard in the Lesser Antilles, because there's large normal faulting earthquakes occurring, as I showed you before, also within the overriding plate that can cause large tsunamis and therefore lots of damage and casualties. So that's it. I look forward to discussing with you during our live session, and for now, thank you.